Welcome to the Explainer. If you've ever wondered how billions of devices securely talk to each other across the internet without total chaos, well, you're in exactly the right place. Today, we're completely demystifying the fundamental 32-bit mathematical foundation of the internet, IPv4. Okay, let's quickly map out our digital city planning journey for today. We'll kick things off with the anatomy of an IP, figure out networks and hosts, and then tour the IPv4 class system. After that, we'll hit multicast and special zones, look at how we literally saved the internet, and finally zoom all the way out for the complete IPv4 universe map. Let's get into it. So, Section 1, the anatomy of an IP, understanding the 32-bit blueprint. We hear the term IP address all the time, right? But let's actually look under the hood at the core logic. The absolute most crucial thing to grasp here is that IPv4, the fourth version of the Internet Protocol, gives us a very strict, uncompromising boundary. We have exactly 32 digital bits to play with, period. Mathematically speaking, 2 to the power of 32 gives us roughly 4.2 billion unique numerical addresses for every single device trying to connect globally. Now check out how this 32-bit blueprint is seamlessly split right down the middle, well, usually the middle, into 2 very distinct sections, the network bits and the host bits. You'll also notice that slash notation at the bottom, something like a /24. That simple little number is basically the key to the entire map. It tells us exactly how many of those 32 bits belong to the network side of things. Of course, computers speak in raw ones and zeros, but we need something human-readable. So we systematically group those binary digits into 4 distinct blocks. That string of binary perfectly translates to the familiar decimal format we all know, like 140.134.10.1. And since each block is exactly 8 bits long, the absolute maximum decimal value any single block can ever hit is 255. No exceptions. Okay, here's a really great piece of insider network engineering knowledge. You might naturally want to call those 8-bit blocks bytes. I mean, it makes sense, right? But in networking, we strictly use the term octet. Why? Well, historically, a byte size could actually vary wildly based on older computer hardware designs. Some crazy systems even use 7-bit bytes. An octet, on the other hand, explicitly guarantees exactly 8 bits every single time. And in the high-stakes world of IP addressing, there is absolutely zero room for ambiguity or hardware interpretation. By relying exclusively on the rigid, uncompromising 8-bit octet, we ensure absolute precision across the entire globe. It's literally what prevents catastrophic, cascading routing errors from taking down the web. Moving on to Section 2, networks and hosts, the street and house analogy. Let's see how organizations like ICANN actually distribute these numbers to pinpoint specific locations online. It helps to think of the network bits kind of like your street name. It tells internet traffic which general neighborhood it needs to navigate towards. Then the host bits act like your exact house number on that specific street. The really cool part is the sliding boundary between them. It dictates the sheer scale of the neighborhood. If you slide it one way, you get a few massive streets with millions of houses. Slide it the other way, and you get tons of distinct streets, but maybe only a handful of houses on each. But there's a catch when assigning these house numbers. You actually can't use every single combination. When the host bits are all zeros, that address is permanently locked. It represents the entire street itself. And when those host bits are all ones, which hits that magic number 255 in decimal, it acts like a giant megaphone. That's the broadcast address, and it's used exclusively to blast a message to every single house on that street at the exact same time. So, this brings us to an ironclad mathematical rule in networking, the -2 rule. No matter how large or small you slice up your network, you are always going to lose exactly 2 addresses in every single segment for those special administrative tasks. Your total available hosts will always equal your total mathematically possible combinations -2. All right, Section 3, the IPv4 class system, exploring the digital neighborhoods. Let's look at how this math shapes the actual structure of the internet by touring its predetermined classes. We start off with Class A. Its very first bit is locked permanently at 0. Now, this class completely prioritizes massive host counts over network numbers. By using only 8 bits for the network and leaving a massive 24 bits for the hosts, a single Class A network yields a staggering 16.7 million usable host machines. Because they're just so massive, these were historically handed out to the internet's earliest pioneers and those giant tech behemoths. Next up is Class B, which kicks off with a leading 1-0. This offers a much more balanced approach, making it the absolute perfect backbone for large multinational corporations. It splits the 32 bits a bit more evenly, 14 for the network, 16 for the host. So Class B gives us exactly 16,384 distinct networks, with each one holding a very robust 65,000 usable hosts. Then we have Class C, starting with a fixed 110. This class swings the pendulum entirely the other way. It maximizes the number of networks to over 2 million, making it highly flexible for everyday distribution. But the trade-off? It severely shrinks each network down to just 8 host bits. Following our golden rule, 2 to the power of 8 is 256, minus 2 leaves us with exactly 254 usable house numbers per network. And that brings us to the ultimate engineering trade-off. It really highlights the absolute rule we've been talking about. As you allocate more bits to the network side to build more streets, your capacity for hosts per network proportionally and rapidly shrinks. It's a completely zero-sum game within the strict confines of those 32 bits.
Let's pivot to Section 4, Multicast and Special Zones, beyond standard communication. What if you need to talk to a very specific group of devices, or safely run tests on your own computer?
Well, enter Class D multicast, starting with the bits 1110, which maps to the decimals 224 through 239. Class D totally abandons our standard street and house analogy. Instead, it creates a specialized one-to-many group delivery channel. A server sends a single stream of data, and only the computers that have actively opted into that exact multicast group channel receive it. It is incredibly efficient for things like live streaming. We also have some essential diagnostics permanently carved right out of the IPv4 space. First is the loopback address block at 127, specifically 127.0.0.1. This is literally designed to securely test your own machine's network stack by routing traffic right back to itself without ever hitting the physical wire. Then we have the local broadcast at 255.255.255.255. Think of this as a device shouting out into the local void the second it connects, urgently trying to discover its surroundings and grab an IP. Okay, Section 5, saving the internet, private IPs, and NAT. We gotta talk about this pressing issue. With only 4.2 billion addresses and tens of billions of smart devices out there, how in the world did we not run out of IPs a decade ago? The unsung hero here is a combination of private IPs and NAT technology, which stands for Network Address Translation. See, ICANN intentionally set aside specific chunks of Class A, B, and C as private networks. These ranges are completely hidden. They're entirely unroutable on the public internet. So an entire office building can use thousands of these free private addresses internally. Then, the NAT router at the edge acts like a master translator, letting all those internal devices share just one single, precious, public-facing IP address to actually talk to the outside world. This is the ingenious trick that literally saved the internet from collapsing under its own weight. Finally, Section 6, the IPv4 universe map, the complete spectrum. We've reached the climax of our explainer. It's time to take everything we've just learned and lay all these puzzle pieces out on one massive global map. This is where the classes, the private IPs, the loopbacks, and the multicasts all slide perfectly into place. Just looking from 0 all the way up to that maximum of 255, you can clearly see Class A commanding the first huge half of the space. You can spot the private IP zones nestled safely inside the standard classes. You've got the loopback tucked away at 127, multicast near the end, and that local broadcast right at the final 255 boundary. Truly grasping this panoramic spectrum is the absolute core of understanding IP4 engineering logic. But I want to leave you with this final, somewhat provocative thought. We have mapped out this incredibly well-designed system, sure, but it has absolute physical limits. In an era where billions of new smart devices, IoT sensors, and connected cars are coming online literally every single day, how much longer can this finite 4.2 billion address universe actually survive? We've squeezed absolutely every drop of efficiency out of IPv4 with tricks like NAT, so use this brilliantly structured 32-bit world as your foundation, because your next crucial step is exploring the massive, next-generation frontier of IPv6. Keep questioning, keep learning, and I'll see you in the next explainer.